1 or 2 more minutes.
Yeah, let's do that.
Period is coming
Yep.
also.
Exactly.
Can I start?
Yep.
All right, hi everyone. Welcome to our, I don't know, it's neither last or the first seminar of this term. I think we're going to just continue having seminars in the next few weeks as well. So, welcome to our seminar. Today we have our own Remy telling us about constraint, reconfiguration, and motion planning. Go ahead.
Thank you. Thanks for the introduction. Thanks everyone for making it today. So in today's talk, I'm going to be going over some of the work that I've been up to. So most of the problems we're going to be talking about have a geometric flavor, but they also have ramifications in both reconfiguration and motion planning. So to start, let's take a look at a bit of a toy problem. So let's say you have a bunch of toothpicks that you throw on a table. These toothpicks lie flat on the table, and you're trying to rearrange them in a specific way. So we're trying to make them more vertical. So what you're allowed to do is rotate a toothpick about its center. So you can't really move toothpicks around, and you're only allowed to rotate a toothpick a single time. So that kind of seems like an easy problem, but in fact, there's a lot of intricacies in there. And beyond the complexity end of things, the reason why we're interested in such a problem is because it falls at the intersection of at least two fields. So on one end, obviously, geometry. Everything about the problem seems geometric. So toothpicks themselves are geometric objects, and so is the way they move. So on the other hand, we are looking at motion planning. So motion planning is a class of problems where we're looking at either one object or multiple objects that move from a state to some other desired state. And I thought it would be a good idea to include the rush hour problem, which you may be familiar with. So in rush hour, the goal is to get this red rectangle into the shaded area by moving around the blue rectangle. So one way of achieving this would be doing something along these lines. So rush hour, among many other puzzle-like problems, has been extensively studied, maybe around 20 years ago. So by comparing toothpicks to rush hour, it might seem to be the case that what we should be focusing on is the geometry that's at the root of this problem. So let's take a look at this. So the first thing you want to think about is what exactly constitutes a rotation that is allowed. So that's a toothpick. And you're only allowed to rotate U clockwise in this case if the green parts, which we call the swept sectors, are vacant of any other toothpick. Otherwise, you'll end up hitting some other toothpick along the way, which isn't allowed. So, I mean, that's already fairly simple. We're not really saying anything that's too complicated at this point. But what's perhaps more interesting is the implication of what I just said. So now let's take a look at the case where we're choosing a rotation direction for U, except that V in its initial orientation is in the way. So this implies that V should get out of the way before we're able to rotate U. So in some sense, we're starting to think about the problem less geometrically and more in terms of partial orderings. So what if we're looking at another case where instead of V blocking U when V is in its initial spot, V blocks U when it's already vertical, keeping in mind that we can only rotate an arm once. So in this case, V has already rotated. So the question is, are we able to rotate U clockwise? The answer to that is obviously not. We're sort of stuck unless we kind of want to like go back in time and get the rotation of U done before V ends up vertical. So again, there's nothing too complicated going on here. Why is this a problem of interest? We've already started going from a geometric view of things to a combinatorial one. And on the other end of things, this problem we're looking at here can be generalized to cover a wide array of motion planning problems, as we'll gradually be seeing. So let's formally define things first. So we won't be thinking about things in terms of toothpicks anymore, because that's too much of a toy problem. We look at robotic arms instead, because that's a bit more relevant to people that are working on motion planning things. So we have a segment with a defined midpoint that is fixed. And what the arm does is that it rotates around this midpoint. So the rules of the game is you can only move one arm at a time, and you may only rotate each arm once. The choices you can make concern the direction in which to rotate things. And your goal is to make everything end up vertical while avoiding collisions, which this is an example of. So obviously that will not be allowed, because as the leftmost arm is rotating, it'll end up colliding with the rightmost one. So let's look at a formal, or maybe a semi-formal definition of the problem. So the problem is single move robotic arm motion planning. So for your input, you're given a set of robotic arms that are pairwise non-intersecting. That's what we call a conflict-free set of robotic arms. And for your output, we're looking at a sequence of rotations that makes everything vertical without causing any collisions. And that would be a collision-free sequence of rotations. So looking at the instance that's here, one way of solving this would be rotating U anti-clockwise, followed by V rotating clockwise, and ending with W rotating clockwise. So as we gradually get a better feel for how things interact, it's a good idea to start with a more restricted version of a seminar, where the robotic arms can only rotate in the clockwise direction. So in some sense, that gets rid of the choice component of the directions, and it makes it possible to just focus on how we want to be ordering these rotations. So the potentially most intuitive thing to think about at this point is let's try to encode what's going on in using stuff we're familiar with, and that's graphs. And that's the encoding we're going for. So for every arm, we'll have a vertex, and we will have an arc from a vertex U to a vertex V if the vertex or whatever is represented by U should be rotated before whatever is represented by V. So there are a bunch of different cases regarding how this could look like geometrically. So maybe the most obvious one would be this one. So here we chose V to rotate clockwise. Clearly, it cannot do that because U's initial orientation is in the way. So that requires us to rotate U before V. So the focus here is that U blocks V's rotation in its initial position. So that's one case. And another case, which is maybe a bit less obvious, is this one. So here, you'll see that V's vertical position is what blocks U's clockwise orientation. So in other words, if V is vertical, U clearly cannot rotate clockwise. So in that case, we would need to rotate U before V as well. And again, that would be represented by this same arc that is at the top. So what's interesting about this other example is we also have a blocking that's symmetrical. In other words, U being vertical will block these clockwise rotation as well. So if we're in the clockwise only realm of things, we're kind of already stuck, because no matter how you try to order these two, you'll end up with a collision. And in fact, we use this to illustrate our first positive result. So that's the instance we just looked at. This is how we would encode this graph theoretically. And that is the interpretation of the encoding. So U must be rotated before V, V must be rotated before U. Obviously, you cannot really satisfy both of these statements at once. So that would be a no instance. So here, our first intuition is compute the encoding, which can be done efficiently, and then figure out whether there's a cycle in this. So clearly, if there's a cycle, you'll end up with a sequence of statements that you cannot satisfy at once. And in fact, as it turns out, that is an if and only if. As in, we have a solution if and only if the encoding is a DAG. I'm not going to bother with the proof of correctness. It follows immediately from what these arcs that are in the encoding mean. So now let's say you have a DAG and you want to compute an ordering. That's fairly simple, right? You just topologically order the vertices and then you're done. So as I mentioned earlier, when we force ourselves to rotate everything clockwise, we no longer have to worry about the local choices. So the problem turns into an ordering problem. Whereas in the more general case, it matters, there's the choice to be made regarding how things rotate. And in fact, if you take the same exact instance and we look at it again, while allowing things to rotate in both directions, that would be a solution. So you can rotate Q clockwise followed by V anti-clockwise. So the problem here is that, if we're still looking at the same encoding, it doesn't really seem like it's saying much anymore, because we have a cycle there, but clearly we were able to solve the problem by allowing this extra rotation direction. So we need to be a bit more careful now once we introduce this extra rotation direction. So there are some distinctions to be made. So we're still using this arc to mean the same thing. U must be rotated before V, except this arc could arise because of different reasons. So the first distinction that needs to be made is the choice of what arc or what arm to rotate is it that's causing this constraint to arise. So it could be either U or V. And then you also need to make the distinction with regards to the direction in which this rotation that's making this constraint show up is happening. So we end up with, in some sense, 4 different reasons for which this constraint could show up. So that might be a bit confusing. So that should be clarified if we start looking at some examples. So in this example, we chose to rotate V. So that's a V rotation, and we chose to rotate it clockwise. And in this case, you can easily tell that U must be rotated before V. So that's a U rotation example where U is rotating clockwise. And again, in this case, U should be rotated before V, because if V rotates first, it will block U's clockwise rotation. And we're going to have the same thing happen symmetrically for the anti-clockwise rotation. So there's an interesting distinction to be made here when we compare V rotations to U rotations. And it's that in the V rotation column, you notice that D rotations are blocked by initial positions. So U's initial position is what's blocking V in both cases. Whereas in the U rotation case, it's V's vertical orientation that's blocking U's rotation. So we rename these and we call them initial position constraint and final position constraint. And when we say head rotation and tail rotation, that is just V and U, right? So V is the head of this arc. So we just call this a head rotation or a constraint that shows up because of a choice of rotating the head of the arc. And the other side would be a tail rotation. So we need to distinguish between these 4 cases. And to do that, instead of having a single directed graph that encodes these constraints, we actually have 4 of them. And I'll be showing you an example for one of them in a second. Yes.
You know, taking each vertex and creating copies, one corresponds to the clockwise rotation, one corresponds to the anti-clockwise, and just connect the previous thing to it.
So I think what we end up doing is sort of what you're talking about. As in, you're saying there wasn't a need to have separate graphs for them. You could have just combined them in a single graph. But then I think it's a matter of semantics.
Like this possibilities for every vertex to the four different types of edges.
Yes. So an edge could basically exist in between two vertices in any of the four graphs. Okay, so let's take a look at this instance to illustrate one of the four directed graphs. So we're looking at the clockwise initial position constraint graph. So we'll start by zooming in on two of our robotic arms. That's U and W. So if W rotates clockwise, it's blocked by U's initial position. So that's why it's a clockwise initial position constraint. And then that requires U to be moved before W. So we have an arc from U to W. So one last thing is that it's W's rotation that caused this constraint to show up. And in that case, that explains why that's a head rotation type of constraint. So then we do the same thing for every pair of arms in here, and we end up with this graph, which again is one of the four constraint graphs. So I skipped talking about the rest, but basically we have two clockwise constraint graphs and two anti-clockwise constraint graphs, which correspond to the same layout we were looking at when we looked at the table a little bit earlier. So now we're kind of looking at this problem in one of two ways. So on the left, we have what we started with, which was a seminar. And on the right, we have this proposed encoding that we introduced. So there are some similarities and some differences between these two ways of doing things. So on the left, our objects are robotic arms. On the right, our objects are vertices. On the left, the choice is some rotation direction. And on the right, our choice is between C and A, or clockwise and anti-clockwise. So depending on what rotation direction we decide to assign to a vertex, that will determine which are the constraints that need to be satisfied in a solution to the problem concerning this specific vertex. So in both cases, the constraints are the initial position and the final position constraints that need to be satisfied for every object and whatever choice it's given. On the left, the solution would be a sequence of rotations that makes everything vertical without causing collisions. On the right, it's an assignment of C or A to each of the vertices, and then an ordering that makes it possible to satisfy all the constraints. So this form that's on the right, we call two compatible ordering. So the two is in reference to the number of choices we have, which are C and A. And it shouldn't be too hard to see that we have a reduction from SMRAM to compatible ordering. It was kind of sketched in some way on the slide. So let's now think of generalizing. So in SMRAM, we have two choices. So we have, for the clockwise case, two types of constraints. That's initial and final. For the anti-clockwise case, we have initial and final as well. So why don't we, instead of having two ways of moving, we look at the case where we have k of them. So in this case, we end up with k pairs of directed graphs. That's I1, F1, all the way until IK, FK. And that is the formal definition of what k-compatible ordering is. You don't really have to bother with the details here, because again, the gist of it is you have those vertices, you want to order them, and you want to label them in such a way that you respect all initial position and final position constraints. So as a direct consequence of the definition of k-compatible ordering, we know that we can solve one compatible ordering in linear time, because that's basically the same exact problem as clockwise only SMRAM. Right? We have a single way of moving per arm, and we're done. So we kind of left out most of the talk about geometry because incompatible ordering is purely a graph theoretic problem at this point. So what we will be talking about in the rest of this talk is restrictions that so that was at least our initial way of thinking about things. We wanted to get as close as possible to saying something useful about SMRAP. So before we get to that point, I think it makes sense to at least motivate why we're talking about K-compatible ordering, because the jump from 2 to K was a bit arbitrary. So the simplest way of seeing things is by considering SMRAM in 3 dimensions. So now instead of attempting to or needing to make something vertical in 2D, we want to move this arm that's sort of in the flat plane upwards. Everything else is kind of the same. We still want to avoid collisions, and we're still moving an arm exactly once. But now, when we say rotation, it's any movement of this arm within the sphere, with its midpoint being fixed, so that it starts the way it currently is, and it ends up sort of perpendicular to the flat plane. So what would basically constitute a way of moving is composing those 2 movements. So you can kind of rotate the arm in the plane, and then you could rotate it upward. So that would count as one of potentially K different ways of moving this arm. Okay, so before we delve into the technical parts, I'll take a quick detour to talk about some things that ought to be defined. So most of our results concern something that we call the union graph. So what is a union graph? It's the graph you get out of unioning the edges that are in all of your constraint graphs. The meaning of the graph isn't exactly too useful, but we talk about structural things concerning it, which is why we're defining it at this point. So more importantly, yes?
As for the 3D, you just make one rotation on some axis, or it could be
so it doesn't have to, it could be anything. It could be arbitrary. You could just move around, zigzag, right?
It's just one.
Yeah, it's just a continuous movement, right? So, yeah. So perhaps more importantly, we need a way to characterize good label assignments. So what exactly is a good label assignment? It's one that avoids cyclical ordering. So what is a cyclical ordering? So if you have some vertices, you give them labels, and these labels make it so that you have a sequence of vertices, let's say V1 until Vm, where V1 has to rotate before V2 has to rotate before V3, all the way up until the end and then back. So that's a bad label assignment. So let's look at a bad label assignment. So that is the core argument we're going to be using a bunch. So we're going to be referring to stuff we've talked about a bit earlier as well. So let's say we've labeled U with 2. So now we take a look at U in both I2 and F2. So the constraints that we need to abide by are the incoming arcs to U in I2, because remember that initial position means a choice on the head is what dictates whether a constraint is shows up or not. So in this case, we look at what's incoming to U. That's V must be rotated before U. And we look at what's outgoing from U in F2, which there's nothing there, so we're happy. Now let's say we're labeling W with 2. Again, we look at what's incoming to W in I2. So that's this arc. And we look what's outgoing from W in F2. And I've just wrote what the interpretation of these arcs means. If you look at these 3 statements, clearly we already have an issue. So V must be before U, which must be before W, which must be before V. That's a cyclical ordering. And we picked a bad label assignment. So what what would then be a good label assignment? So let's label U with 1. So now we're looking at U at the top. Arc that's incoming, that's VU. Arc that's outgoing, that's UW. So those are the two constraints that need to show up in a solution. And then I picked labels for W, for V and W that don't cause any constraints to show up. So for V, that's labeled 2. That's here. There's nothing incoming in I2, nothing outgoing in F2. We're happy. As for W labeled 1, there's nothing incoming in I1. There's nothing outgoing in F1. So clearly, if that's the only thing you have to satisfy in a solution, you can easily do that. So no cyclical ordering, meaning that those are labels that allow us to order things in some way to get things to work. Okay. So to start, we look at a hardness result. So the question is, I mean, the idea here was to try to push things as far as possible without sacrificing hardness. So what we ended up with is 2 compatible ordering being NP complete when the union graph is planar and has degeneracy 3. So remember, as I mentioned, those results will be saying stuff about the union graph. So let's take a look at what the reduction looks like. So first, that's a reduction from planar for bounded 3-sat. In case you're not familiar, that just means planar 3-sat where every variable shows up in at most 4 different clauses. And we'll be looking at what's on the right as our illustration for what the reduction looks like. So let's start with the easy part. For the vertex set, so in phi, which is our Boolean formula, we have 4 variables. We'll have 1 vertex per variable, and we have 6 literals. We also have 1 vertex per literal. So the variables are at the top of each of the 4 directed graphs, whereas the literals are at the bottom, and they're sort of grouped in triangles just to make things simpler. Okay, so planar 3-sat is if you have so if you construct a graph out of 3-sat where your vertices are the variables and the clauses, and you connect the clause to a variable if the variable shows up in the clause, then if that's planar, then that's planar 3-sat. Okay. So for the edges, I sort of split them up into 3 sets because every edge set sort of serves a particular purpose. So to start, we will connect the literals of the same clause with diagonal. That's what you're looking at the bottom. And the purpose of doing this is so that we force that in a solution, at least one of these 3 literals is not labeled 2, because if you label everything with 2, just given the interpretation of these arcs, you'll end up with a cyclical ordering, which wouldn't be or would not exist in a solution. So the existence of whatever is at the bottom already says that in every clause, we have a literal that is labeled 1. So as you might start imagining, the reason or the interpretation of a literal being labeled 1 is that this is a literal that's satisfied. So the rest of the edges or the arcs we're going to be adding are to make sure that the choices on their variables make sense. So if we have a literal that's satisfied, the variable is given the correct truth value. So I removed the red arcs and I introduced some blue ones. So these blue arcs connect a positive literal to its variable, and it does so across I1 and I2. So there's one arc in I1 and another arc in the other direction in I2. So the point of these arcs is if we have a clause that's labeled 1, that's going to force 2 things on its variable. So first, its variable has to show up before it. And second, its variable also has to be given the label 1. So to illustrate, let's look at C11. So let's say C11 is labeled 1. The existence of this edge that's incoming means that X1 should show up before C11. So that already takes care of this part. So why should x1 be labeled 1 if it's not? So let's say x1 is here instead. This arc means C11 should be before x1, but we already know that this arc means the other direction of things, and then we end up with a cyclical ordering. So it must be the case that if C11 is 1, then x1 is also labeled 1 and comes before it. So that is meant to be interpreted as x1 is, in this case, set to true. And we have something symmetrical happening for the for the other side. So if C12 is labeled 1, x2 cannot be labeled 1, because if it is, we have an arc going from here to here and then back. That's a cyclical ordering. So consequently, it has to be the case that x2 actually ends up being given the label 2 and appearing after C12. So positive literal labeled 1, its variable is also labeled 1. Negative literal labeled 1, its variable will be labeled 2. And that's all of the arcs at once. So I aggregated the observations that we just looked at. And let's look at how a typical solution would look like. So we said that there's at least one literal per clause that's labeled 1 without plus generality. Let's assume that this is C13 and C23. Now we're going to use the second and the third observation to say that for C13, since its variable is x3, that should be labeled 1. For C23, since its variable is x1, and since C23 is a negative literal, its variable should be labeled 2. So all what's left to do is anything that's labeled 1, you set to true. Anything that's labeled 2, you set to false. And you have your satisfying assignment. So there's going to be some variables that aren't really associated with any of the literals that are labeled 1. And that's fine. You could just give them any truth value and then you're done. So to summarize, that's sort of an abridged version of the logic. So for every clause, you have one literal that's labeled 1. And what you're going to be doing is assigning a truth value to their variables. So the problem is, what if there's a variable that kind of shows up because of two different literals? So we have x that's labeled 1, and then we have x bar that's labeled 1 elsewhere. So that is something, and that's the only issue that's kind of left and that we need to resolve. But if that's the case, because of these two observations, one of them is going to say label the variable x1, and the other one is going to say label the variable x2. But that cannot happen. So we know for a fact that those literals that are chosen to be labeled 1 cannot be like polarly opposite. So we cannot have an x and an x bar that are both labeled 1. So then we're happy. So that concludes the backwards direction. So for the forwards direction, what we do is as I mentioned earlier, the goal is to label things in a way that avoids cyclical ordering. So where could cycles show up? So we're fortunate enough that in our construction, the cycles are the obvious ones. So there's the red cycle that's at the bottom. There's this bidirectional arc that's in F1. So that's another cycle. And the third cycle is across I1 and I2, and it's due to the blue arcs. So the blue arcs connecting the same variable and literal, their union would constitute a cycle across I1 and I2. So the solution that we propose is what we're looking at here. So we'll include the variable set to true first, and we'll label these one, followed by the satisfied literals, followed by the unsatisfied literals, and at the end we'll have the variable set to false that are labeled 2. So we'll narrow down on what's interesting about this solution as we look at the cycles that might cause cyclical orderings, which we're trying to avoid. So starting with red cycles. So earlier we said we have an issue with these if everything is labeled 2. If we look at this portion that's highlighted in the solution, so there must be one satisfied literal per clause. So we know for a fact, if you pick any triangle, one of the three will actually be at the top. So then we avoid our cyclical ordering. So that's the reasoning for red cycles. So you never have a triplet, a literal triplet of the same clause where everything is labeled 2, due to the way we define the solution at the top. So as for blue and gold cycles. So let's take a look at, so let's say that C13 is satisfied. So it's labeled 1. So that's a positive literal. For it to have been satisfied, its variable should have been labeled 1. So in that case, we know that x3 is true. So if it is true, in our solution, we label it 1. So here we have an issue if a literal is labeled 1 and its variable is labeled 2 if it's positive. So we know this is not a problem. And it's a bit of a mirrored argument for the gold cycles. So let's say C23, which is a negative variable now, is what's satisfied. So it's given labeled 1. Since it's a negative literal, for it to have been satisfied, its variable should have been set to false and given label 2. So we do not have a cyclic order in this case either, because that would happen if the variable was labeled 1, which it's not. So we're also happy about that. So we know that neither the blue or the gold cycles cause cyclical orderings in this case. Okay, so that's the main hardness result that I wanted to present. To move forward, let's look at what positive results we can obtain. Starting with sparse instances. So when you think about sparse instances, typically what comes to mind is maybe union graphs that the case where the union graph is a path, a tree, or is sparse in general. What you typically start looking at is the case where the union graph has bounded treewidth, and for that we have so in case the treewidth is bounded, we have a polytime algorithm, or in other words, k-compatible ordering is actually FPT when parameterized by k plus t. So at this point, it's worth mentioning that this algorithm is constructive, so it's not a consequence of Courcelle's monadic second-order logic meta theorem. In case you're not familiar, that's an easy thing to state. What this meta theorem says is if you're looking at a graph property that's expressible in monadic second-order logic, then if you have bounded treewidth, you have a linear time decider for it. So our algorithm, I mean, we actually have an algorithm, we're just using Courcelle, and most of the reason why that's the case is because we're kind of, typically when you're in a setting where you're looking at permutations of things, it's not entirely clear how you can express things in MSO terms. So that's sort of the more obvious positive result. So next, what we'll do is we look at the other end of the spectrum. So what if we want to see what we can say when our union graph is dense? So on the right, you're looking at a graph G, and I've partitioned this graph into 4 sets of vertices, and you can see that there's some uniformity happening here. So those partitions I'll actually call modules, and you'll notice that if you pick any pair of modules, the vertices are either complete or anti-complete to each other. So between 2 modules, you either have all of the edges or none of them. So that makes it possible to come up with the process that's called modular decomposition. So you can basically do what I just said recursively, and you end up with a tree. And what's interesting about this tree is that it allows us to introduce some measure that correlates, or that is correlated to the modular decomposition tree of a graph, and that would be the modular width. So that would be the maximum number of partitions that you're splitting your graph into at any given point throughout this process. So the tree is really complete here, but it should be fairly convincing that you do not really hope to get anything that's bigger than 4 as you go down, because your modules are already fairly small. So the idea was to try to look at the union graph and say something concerning modular width or modular decomposition. The problem is we have a lot more information compared to just a non-directed graph. So we can't really just apply what we know about this stuff, which is typically used in the context of parameterized algorithms directly in our case. So the idea was to basically come up with a variant for this, which we're calling labeled modular width. So here, what we're doing is we're orienting the edges and we're labeling them based on the constraint graphs that they come from. So that graph that's there, I just transformed it into another version where the arcs are oriented and where the arcs are labeled based on the constraint graphs from which the arcs come from. So everything else is sort of the same. We're still decomposing and we still do this process recursively. Okay, so as it turns out, we have an FPT algorithm when we parameterize by K plus LMW, where LMW is the labeled modular width of the union graph. So the idea of this algorithm is, as is typically the case, we want to be doing some DP on the modular decomposition tree. So the state, the DP state that we're interested in is, so we're going to have something that's called a feasible label set. So a feasible label set is a set of labels that is used in some way in a solution to an instance that's restricted to one of these modules. And we're going to have a bunch of these. So that would be your cursive as at the bottom. So the idea is we're going to compute these for the modules. So that's cursive L1 up until cursive L4. And then this is going to be used to compute cursive L, which is the family of feasible label sets for the graph G at the top. And obviously, we have a yes instance if the feasible or the family of feasible label sets for G is non-empty. Okay, so let's delve into the specifics a little bit. So obviously, we're going to have an induction on the size of these modules. So if you have a module that's on a single vertex, there are no constraints. You could label the vertex using any label that's anywhere from 1 to k. So that would be your family of feasible label sets. So things get a bit more complicated when you already have your feasible label sets for the modules and you're trying to compute your family of feasible label sets for G, which sort of aggregates all of these together. So the idea here is we'll be looping over every combination of the feasible label sets for these that are in here. And then we figure out which of these arcs will have to be included depending on the labels that are used within each one of these modules. So that's a lot easier to explain via an example. So let's say we considered L1 from this family, L2 from this family, L3 from this family, and L4 from this family. So this module here is using label 2. So out of the arcs that are coming in and going out, the ones that survive or that should be added are I2 if it's coming in, or F2 if it's going out. So that's the same logic we had when we were talking about cyclical orderings earlier. So in this case, we end up adding nothing. Now, if we look at L2, so L2 is 2. So is there an I2 coming in? There is. Is there an F2 going out? There isn't. So we end up including I2. And we do the same exact process for everything else. So here, for L3, there's an F2 going out, and then we realize that there's the label 2 being used here. So that's a constraint that goes across modules. And we do the same thing for L4. So this is an acyclic. So this graph or this digraph where the vertices are the modules is acyclic. And that's good because you know these are feasible label sets. So to get a solution for G, all you have to do is solve using those feasible label sets and then topologically order the solutions based on what you ended up with. So in this case, you would solve G3 using that feasible label set, and you would follow it by, let's say, G4, G1, and G2. So if the digraph is acyclic, we're happy, and we end up including the union of those labels in the labels or the feasible label sets of G. So now the issue is, what if we end up doing this exercise and we end up with some cycle in this diagram of modules? Are we doomed, or do we just skip this union of LIs? So the answer is not exactly. There's some nuance that's going on here. So a cycle isn't enough to say we end up with a cyclical ordering. So let's take a look at this example. We picked L1 out of cursive L1, L2 out of cursive L2, L3 out of cursive L3. And by applying the same exact process to figure out what arcs to include, we ended up with a cycle in here. So now here, the distinction is these arcs, so the I2 coming in here and the F1 going out, they connect to two different vertices in the middle. Because this I2 was due to a vertex being labeled 2, which is due in this case, whereas this F1 coming out is due to some vertex in G2 being labeled 1, which is this vertex. So we cannot just say we have a cycle, therefore, that cycle is going to traverse this module and then we're stuck. In other words, we kind of need to look in more detail at what this module internally looks like under this choice of labels. So if we know for a fact that these edges or these arcs were added due to a single vertex in every module, obviously we're stuck and we end up with a cyclical ordering, but that's not really the case. So not only do we need to keep track of our family of feasible label sets, we also need to keep track of whether there exists a solution where, let's say in this case, U does not forcibly come before V. Because if there is, and if the solution uses L2 as in here, we're happy. So we can sort of break the cycle and say we can use this union of labels for the entire instance. So that's an example where we have an arc that isn't included. So F1 here means that this arc would be a constraint we need to worry about if U is labeled 1, which it's not. So no cyclical ordering here, assuming everything else is a cycle except this part. Whereas in here, we have an I1. So if this arc is an arc that is in the graph I1, and if V is labeled 1, that's an arc that gets added, and then we end up with a cyclical ordering. So when I said we're only keeping track of families of feasible label sets for every module that wasn't exactly accurate, we also need to keep track of for every pair in every module, whether there exists a solution using a specific feasible label set that does not force, in this case, let's say U to come before V. And that was a bit easy because there's just a single arc between them, but you could have a case where you actually have a path. And the good news is this is still efficiently computable, and we're happy. I'm not going to go into the details because that's already complicated enough. Okay, so this concludes positive results. So let's sort of summarize what we did. On the positive end of things, we presented an efficient algorithm when we had two examples of bounded parameters, that's treewidth and labeled module width. On the other hand, for hardness, we got NP-completeness when the union graph is planar, has bounded degree, and has bounded degeneracy. And as a bonus, we actually managed to make each constraint graph acyclic as well. So remember in the construction, we had those blue, red, and gold cycles, which were kind of looking a bit suspicious. We were able to get rid of these, and hardness was still maintained. So remember that we started with SMRAM. So what can we say about SMRAM at this point? The bad news is we cannot really say anything. In the case of SMRAM, if we look at their encoding in two compatible ordering terms, the union graph is a spanning subgraph of what we call a unit disk graph. So what's a unit disk graph? So if we start with a drawing of some circles in the plane that have the same diameter, and you have a vertex for every one of these circles. So if two circles intersect, you just add an edge between their vertices. And there are a few things that are known about unit disk graphs, but none of what we already know kind of helps us with the information that we were able to aggregate at the top. So in fact, you can come up with SMRAM instances with unbounded treewidth, unbounded modular width, And you can also easily figure out that there are some instances of SMRAM that we know nothing regarding how to deal with them. And they're sort of a subclass of this class that you're looking at to the right there. So we were not able, so that was our initial goal. We wanted to get something out of looking at state pattern ordering. We were not able to do this. Now, the good news is we were able to settle the complexity of SMRAMP using completely different tools. So that happened a bit later. That's probably something I'll be talking about in my next talk. So, and the impressive part is that this is the case even when everything is initially horizontal as well. And even the interactions, so there's not too many interactions involving the robotic arms. We ended up with an NP completeness result for that. So what do we have at this point? Clockwise SMRAMP is easy. SMRAMP is hard. So what do we want to look at next? What is it that makes SMRAMP hard? And how can we sort of change some things about SMRAMP so that we get something that's a bit more interesting than what we currently have? Because right now the problem is kind of dry, right? You have this ordering or like this ordering aspect of things, and this decision on how to rotate things. So we want something that's a bit more expressive. So our first instinct was to allow multiple moves per robotic arm. And that's what we call multi-move ramp. So this is fairly easy to go over because it's not much different from what we've already seen. The difference is now we have a set of admissible angles, which we can rotate back and forth in. And the final angle doesn't have to be vertical anymore. So you have an initial angle, and then you can move back and forth between any of your admissible angles. The goal is to make everything to make every arm get to its final angle. And the constraint is still that we want to avoid collisions. So why do we care about MMRAMP? Because it seems like we're just milking the problem at this point, right? So as it turns out, MMRAMP has some uses beyond being a generalization of SMRAMP, and it's that it's a reconfiguration problem. So it took us a while to get here, because that's sort of part of the title of the presentation. But we eventually did get to where we want to get. And for those of you who aren't familiar with this, reconfiguration, briefly explained, is when we're looking at some problem and some solution to a problem, and what we're looking to do is to go from one of these solutions to another. So we're calling a solution a configuration, and what we're allowed to do with a solution is what we call reconfiguration step. So that was coined, or these terms were coined not too long ago. It's been like 15 years now. So if you want to look at MMRAMP in the context of reconfiguration, that's what it kind of looks like. So a configuration would be a set of robotic arms that does not have any intersections, and the reconfiguration step is just rotating one of the robotic arms. So why did we get here? So we're kind of using MMRAMP in some way to join SMRAMP and its graph theoretic encoding to the graph reconfiguration realm of things. So most of the work that's been done in reconfiguration deals with graph reconfiguration problems, and we've been seeing some similarities when it comes to how we can treat the geometry end of things versus the graph reconfiguration end of things. And we're hoping that we eventually be able to transfer some of what we're figuring out from the geometry end of things to push the frontiers of what we know in graph reconfiguration further. So even for MMRAMP, we actually have some results that I will be going over. So we get p-space completeness even when we restrict both the number of angles per arm and the total number of distinct angles used across all of the arms in the instance. Yeah, that requires a lot of talking to go over. So I'll be wrapping things up now. So to kind of summarize, beyond the discussion between SMRAMP and MMRAMP, one thing we want to be looking at is a more fine-grained perspective of SMRAMP or MMRAMP, and that's mostly dealing with some interesting parameters. We've already seen one of these that's labeled modular width. So unfortunately, we know nothing about labeled modular width except its definition, because that's something we introduced ourselves. So the hope is to kind of see whether we can say something about computing it, knowing that regular modular width can be computed in polytime. More generally, it would be interesting to see if we kind of look at some slightly different motion planning problems, whether we can extract some density parameters that could give us some insights regarding how the encoding of their constraints look like. So we want to look at k-compatible ordering and see whether there's anything of interest to these graph classes based on the motion planning problem we're looking at. More generally, we want to look, and that's a bit of a shorter term kind of thing, generalizing both of these problems. You can increase the dimensions. You can have arms rotate at the same time, or you can also allow arms to continuously kind of change as they're rotating. Maybe have them like shrink or expand, and then sort of do all sorts of funky things as they're rotating. Yeah, but as a long-term end goal, the hope is to reconcile some of our results with some of where people are stuck in terms of graph reconfiguration problems. That's the end of the talk. Thanks.
Questions for me?
Yes.
So real robotics, would you use synchronous movements?
Yes.
And you have to be going at different speed. It seems there are a lot of examples that you gave that would be solved if you were allowed to do that.
Yep.
Does the problem generally become easier if you allow simultaneous motion or absent? About that.
Okay, so well, what's out there? So there generally there's not a lot that's known in terms of provable results. So typically, when you're dealing with robots that move synchronously, it's typically some heuristic results that are out there. So I mean, one of our goals was to sort of formalize what's going on exactly, and that's why we started where we started. But otherwise, I am not aware of any clean hardness results or clean positive results in that regard. But it's definitely clear that there are some instances where allowing things to move at once makes things that would have makes no instances yes instances. So that is, I mean, that's even easy to figure out as well. So yeah, but yeah, that is one of the directions we'll be looking at. Yes.
So in SMRAM, discretize the problem, right?
Yes.
To have the initial configuration, and the only thing allowed to do is move to the final configuration. So what happens if you allow continuous rotation, right? That you say, okay, I love my arm to rotate the way that something else is going to move. These kinds of things. How does the problem change?
Okay, so I'm assuming you're already allowing multiple rotations, but
Yeah.
even though, so I mean that's good.
You can rotate continuously because even in it was a discrete set of admissible angles.
Yeah.
But imagine sometimes these things could be continuous.
Yeah.
So how does the problem change there?
So I mean, obviously, so I haven't really showed that, but even if we just look at SMRAM and MMRAM, the way we define them, you already have instances that become solvable because of MMRAM. So now you're sort of trying to push this a bit further. So now you're kind of saying, even in MMRAM, we're not really discretizing things. We're sort of looking at the more continuous aspect of things. So, I mean, if I were to guess, like that becomes not interesting very quickly, right? Because, I mean, if we're discretizing, let's say it's at a 1 degree type of discretization. So, I mean, this doesn't really change much beyond, I mean, if you switch from that to something that's completely continuous, I think you'd just be struggling with encoding things more than anything. Right? Like it sort of becomes a completely different realm. That would be my guess.
Is anything known?
No, nothing. So there's nothing, to the best of my knowledge, that's sort of known about. At least, again, assuming we're talking about this specific problem. obviously there are a bunch of problems where you're doing continuous motion and things make sense there. But yeah, I mean, this problem is something that we came up with ourselves. So yeah, and most of our focus is kind of trying to see whether there's anything insightful about it, but that could be carried over somewhere else. Thanks.
That's not